All right, so here we have the last problem of homework 6. And right off the bat, it looks pretty intimidating. There's a lot going on here, but if we break it down into individual steps, it's not too bad. So we have a backhoe here, which is trying to lift like a tile down here, and it's powered by these hydraulic cylinders on the arm. And we are trying to find the forces in each of those cylinders. So it gives us this load down here, P equals 2 kips, and then it gives us an angle of 45 degrees. And from here, we have to solve for the force in CG, the force in AD, and the force in EF. Okay, so how we would start this is we should try to find the component of this mechanism that we know the most about. And so that would be this bucket, because we know the force that is being applied to it here. So if we draw the free body diagram of the bucket itself, it would look something like this. Up to here, and then it would go like around. And we've got H in the middle here, and G up here, and then J here. And so P is applied at J, just like in the picture that's given, with its 45-degree angle there. And then we have this 8 inches from from J to H. And then we see that H is a pin support, so it'll have an X and Y reaction force. And it's not a two-body member here that it's connected to. A two-force member. So a two-force member is like these hydraulic presses where there's only forces on each side here. And so we know that the force has to be inwards or outwards along the direction to prevent the rod from starting to like spin uncontrollably. So this arm attached to H is not a two-force member because it has all these forces here. So we have to consider the X and Y component of the reaction. However, at G, we can take this direction here of the CG member, and we know that the force is either going to be inwards or outwards in that direction. Okay, so if we then, draw out the rest of our measurements here, we have 10 inches from H to G, and then from G down to H, we have 10 inches here, and then from H to J, 16 inches. And then we can take the moment about H so that we don't have to worry about these reaction forces, and we can just try to find FCG. Okay, so moment about H is equal to 0. And what we'll get is the X component of P has this 16-inch moment arm, and it's going in the counterclockwise direction. So 16 inches times P X, and X would be cosine theta. And then the Y component will also be counterclockwise and have this 8-inch moment arm. So we would get plus 8 inches P sine theta. And then now we can worry about FCG. So FCG is going to have also an X and Y component. The X component has this 10-inch moment arm. Same with the Y component. So now we just have to find the direction of the X and Y components themselves. So we know that the force acts along this direction, right? So if we find the direction vector for that, it goes up in the Y-axis 60 inches, and then it goes backwards in the X-axis 45 inches. So our direction vector from G to C is going to look like this, negative 45 inches, and then 60 inches up. And then our unit direction vector from G to C is going to just be that 60 inches divided by the magnitude. Right. And what we find is that is just going to equal negative 0.6 and 0.8 here. Okay. So now we can isolate the x and y components of FCG. So the x component is going to have this 10-inch moment arm and be counterclockwise, as I said before. So it'll be 10 inches times 0.6 FCG. And we don't include the negative here because we already determined that if it's going this direction, it'll be counterclockwise. So it has to be, it'll be positive. And then the y component will contribute this, 0.8 FCG here to the moment. And then if we isolate FCG just using algebra, we get a value of 2.42 kips. And it would be pointing along this direction into the member, so it would be a compressive force. And there you go, you found one of your hydraulic press forces. Now we should find, so what we can do now is we can draw the free body diagram of this, this whole part of the mechanism to find the force in member AD. So if we do that down here, we get something that looks like this, and then there's this component, goes down to the bucket, and then up like this kind of. And then the only external forces that we have here are the reactions at B, the reaction at A, and then the force that is applied at J. So our P, and we have theta here, and then our B, Y, and BX, and our A along the direction of AD, FAD, like that. And it's along the direction because, again, this is a two-force member. Okay, so from here, what we can do is we can take moment about B so that we can ignore the X and Y components of this reaction and just focus on FAD. So first, let's find the direction of FAD. So we have that it's along this line, and it travels 48 inches in the negative X direction, and then it travels 36 inches in the negative Y direction. So our direction vector from A to D would be like negative 48 inches, negative 36 inches. And then our unit direction vector be, again, just that divided by the magnitude. And that would be 36, oops. Just to calculate out that number real quick. 6 squared root 16. We get that this is equal to negative 0.8 and negative 0.6. Okay. So now we have the X and Y components of FAD, and we also know the X and Y components of P because we're given that angle. So we can do moment about B equals 0, and then with just a little bit of geometry, we can find the distances here. So we have 42 inches from B to J. And then we have up here 10 inches. And then from J to B vertically, we have 86 inches. And then from B to A vertically, we have 12 inches. Okay. So to start this out, let's see the px component. So that'll go in a counterclockwise direction, and it'll have moment arm 86 inches. So it'll be 86 inches times p cosine theta. And then the y component would actually go in a clockwise direction, so it'd be negative, and it would have moment arm 42 inches. And then that's times p sine theta. Okay. The x component of FAD is going to be counterclockwise about B, and it'll have a 12-inch moment arm. So 12 inches times the x component, which is 0.8 FAD. And then our y component of FAD is going to be counterclockwise as well, with a 10-inch moment arm. Inches times 0.6 FAD. Okay. And then if we use this to isolate our FAD and plug in the numbers, we get the FAD is 3.99 kips. And again, since it's positive and it's pointing inwards towards the member, that is a compression force. Okay, just like that. And then we only have one more force that we need to look for. So I'll draw it out over here. So if we draw this entire system here as a free body diagram, as a rigid body, and then just have this hydraulic press exerting an external force, it should be not too bad to find the force in that member. Okay, so we have the arm here. I'm just going to simplify it to kind of just a shape like that. And then we have our point E, move it up a little bit, E here. And our force EF is going to be along the direction of EF here. Then we have our load just like before, theta. And then we also have a reaction force at I. So we have IY and IX. Okay? And then from here, the important measurements that we need are from I to E. In the Y direction is 18 inches down to point J is 28 inches. And then across right here from I to E, across all the way here is 120 inches. Yeah. Okay, and then we should find the direction of EF. So we have this direction right here, and it goes in the negative X direction 40 inches, so negative 40 inches, and then negative 16 inches in the Y direction. So our direction vector is like negative 40 inches, negative 16 inches. And then our unit direction vector, EF, this one's also EF, is just, again, that divided by its magnitude. Calculate that out again real quick. Squared plus 16 squared, square root. And we get something like this. So negative 0.93. Then here we get 16 divided by this. we get negative 0, negative 37.1. Okay. Actually, hold on, let me double check. Yeah, that's incorrect. Okay, negative 0.37. Okay. So here, now we can take the moment about I, again, just so that we can ignore the IX and IY components, reaction forces. And then this would result in the PX value with a 28-inch moment arm going counterclockwise. So we have P 28 inches times P cosine theta. And then the Y component will go clockwise, so that'll be negative, and it'll have a 120-inch moment arm. Inches P sine theta. Okay, and then our EF X component is going to be counterclockwise with a 18-inch moment arm. So plus 18 inches times 0.93 FEF. And then our Y component is going to be clockwise, so negative, with a 40-inch, I believe, yes, 40-inch moment arm. I'll draw that one out real quick. 40-inch. Okay. So counterclockwise, 40 inches times 0.37 FEF. Okay. And then at this point, if we again isolate FEF, just using algebra, plug in the theta and the P values, we get that our FEF value is 7.79 kips. And we actually get in this case that it is negative, so that means that our actual force will be pointing this way, resulting in a tension force for our component. And with that, that is the last answer for homework 6, and there you go.